So, hallo in die Runde. Da sind wir wieder, da bin ich wieder mit einem neuen Webinar aus unserer Reihe Mittelstand meets IoT. Heute möchte ich ein ganz tolles Projekt vorstellen, Apache IoTDB. Das ist ein relativ junges Projekt, was erst seit kurzem oder relativ kurz im Apache Incubator ist, was sich rasend weiterentwickelt. Und ganz tolle Möglichkeiten mitbringt, vor allem jetzt im Bereich Edge Computing oder Datenanalyse am Edge, wenn man wirklich beschränkte, also Constrained Devices hat. Ich würde noch ganz kurz warten, weil noch einige Teilnehmer fehlen. Ich habe vorhin mal kurz die Liste durchgeschaut und habe festgestellt, dass es doch den einen oder anderen gibt, der immer wieder kommt. Das freut mich natürlich total. Denn offensichtlich hat es einen kleinen Mehrwert hier, unsere Webinarreihe. Da freue ich mich natürlich besonders drüber. Wir haben das Webinar von letzter Woche auf diese Woche verschoben, aus dem simplen Grund, weil wir letzte Woche ganz wenige Anmeldungen hatten. Hier sind ja auch gerade Osterferien und ja, vielleicht hatte der eine oder andere doch irgendwas geplant zu tun, was er jetzt trotz Corona oder ja, wegen Corona doch gemacht hat oder sich mal mit anderen Dingen beschäftigt hat. Deswegen haben wir es auf diese Woche gelegt, weil das sollen ja nicht nur aufgenommene Videos sein oder Streams, sondern letztendlich wollen wir ja schon auch ein bisschen mit euch interagieren und wollen auch die Möglichkeit geben, Fragen zu stellen, dass man wirklich auch ein bisschen was mitnimmt. Ich würde jetzt mal schon mal starten mit so einer kleinen Umfrage über das Thema Abspeichern von Zeitreihendaten. Also wer das heute schon tut oder schon mal getan hat, darf gerne abstimmen, was er denn dafür so verwendet. Da gibt es ja verschiedenste Möglichkeiten, sei es eine ganz normale Datenbank, natürlich ja, Platzhirsche wie InfluxDB oder auch die Cloud-Provider haben ja da eigene Datenbanken für. Vielleicht noch eine Besonderheit zum heutigen Webinar. Das Webinar wird teilweise in Englisch sein. Das hat letztendlich den Grund, dass ich nachher noch Unterstützung bekommen von Xiangdong, also einer der Initiatoren des IoTDB-Projektes, der aus China kommt und Englisch spricht, aber nicht Deutsch. Das heißt, wir werden mal schauen, gibt es denn jemand, gibt es denn jemand, für den es wirklich ein Problem ist, wenn wir den größten Teil des Webinars Englisch sprechen? Weil ich denke, für die meisten Leute sollte das relativ geläufig sein. Hoffe ich doch mal. Es meldet sich zumindest niemand bisher, herrscht noch Stille im Chat. Okay, ich würde sagen, wir legen jetzt mal los und starten rein ins Webinar. I will switch to English then, and we start as usual with the roadmap. We started on the bottom left, and you see we already talked about PSC4X, and we already talked about Eclipse Ditto, which is an excellent tool to store, let's say, the current state of your device. Which also provides some kind of history, but not in the sense that we will discuss today, in a time series sense. Here some facts related to the IoTDB project. I was the first new committer, the first elected committer after the project joined the incubator. I was elected the first PPMC member. I did not contribute that much code. I mostly helped with spreading the word, doing release. I did the first Apache release. And I did multiple talks together with Xiangdong already at the ApacheCon North America, at ApacheCon EU last year, that some may have seen, which are also, I think, available on the internet. Today, I will not only talk about the project in general, technically, but also, again, we will do some live coding or hands-on working with the project in the second half of the talk, of the webinar. Xiangdong is not yet here. He's currently fighting with travel or with traffic jams. He will join us in some minutes. He may or may not be known to everybody. He is working as a postdoctorate assistant researcher at Tsinghua University in Beijing. The Apache IoTDB project was initiated by this university and brought to the Apache Foundation. He has a long history of working with time series data. With big chunks or big amounts of time series data. He has a large history of doing with Cassandra, and so time IoTDB is, in a sense, one iteration of the learnings that Xiangdong and his group had with other solutions. He's one of the core developers, I would say, of IoTDB, one of the initial committers, and he does a lot for the project in providing English-speaking content, as the community really is kind of split between some kind of language barrier, because there are many people in China contributing to the project, and not everybody speaks that good English. On the other hand, nearly nobody outside of China speaks Chinese. So we try to do as much as possible in both languages and translate in between to help to include everybody in the project. So we start with the introduction to IoTDB. This is the mission statement you can find on the homepage. The first thing you see is a database for Internet of Things. I mean, this is a well-known subject, or rather buzzword. And what you usually want to have when working with data from various things is some kind of management specific for time series data. I will say something about the specifics later on. Of course, it's important to take care of collection, storage, but also on analysis or working with the data. One thing that is especially nice with IoTDB is its lightweight architecture. I already said initially that it's nice for working with constrained devices. Many tools we already know, like Iot Db, Open Time Series Database, come from the cloud side, and you would never run them at the edge or on constrained devices, as they're just too powerful, because they rely on things like Cassandra, for example, at the backend, which just doesn't make sense to run it on an edge device. But on the other hand, it also has a nice integration into the, let's say, traditional big data field with Apache Hadoop, which still is a thing, Spark and Flink. So although you can easily and lightweight capture data, you have a good interface to bring these datasets to powerful processing engines for offline processing, basically. The project, as I said, is rather young. It came in the incubator 1.5 years ago. And the aim, as I said, is to, in the end, gather everybody working in the field together in an open source project to get rid of the best time series database for IoT applications. You see an overview of logos from people that work with the project or contribute to the project. Currently, most of the contributors come from the Tsinghua University, who initiated the project. But we are really starting to see diversification in the community as more and more organizations adopt IoTDB. What are important features that IoTDB provides and that you need? One thing that is especially interesting, and I would say nearly the most, is persist data efficiently. Not just persist data, but persist data efficiently. One point is with low processing time. So you can process large amounts of incoming data sets easily. And the other thing is efficiency with regard to space. So you want to store lots of data sets on, for example, constrained devices. So you need to be memory efficient. Of course, preparing data with low latency is important for things like visualization or working with the data sets. Another crucial thing is exclusive operations on time series data. There are specific things you usually do with time series data. For example, downsampling for visualization. If you have a big amount of data, for example, every second or millisecond, you get data from devices, simply because you can, or you may have use cases. But then you want to do a simple visualization of the past day. There's no way of shipping all millisecond data to the front end for visualization. So you have to do the downsampling somewhere in the back end, and the nearer you bring it to the data, of course, the more efficient it will be. Then the integration I already talked about. This is crucial for defining or doing additional services on top of the data. And what's called here life cycle of data is really the concept of integrating everything nicely together, whether it comes from an edge device or is directly running in the cloud where data is imported. It has a command line interface, but also nice programming interfaces, as we will see later on. Yeah, from edge to cloud, run IoTDB everywhere. Basically, you can run, or the default behavior probably of IoTDB is just to run the IoTDB server, either on a cloud setup or on-premise as a server, which has several defined interfaces, how to ingest data, but you also have the possibility to use it on a constrained device, like a Raspberry Pi in this example, and to not use the server, but just a file. The file format is called TS file. I will talk about it later on. But just use this TS file, so just dump your data to a file, no background process needed, and then later on batch import this file to the server. And this gives you a lot of possibilities and opportunities. So we come to the concepts of IoTDB. This, in a regular database system, this would be schemas and tables and namespaces and all those things you, of course, know. But as IoTDB is targeted at IoT and time series concepts, it's a bit different. It has four main notions, or main words you have to understand. The first thing is a device, and a device is usually the representation of the physical device you talk about, or you want to store data. You have a measurement. This is something which is below the device level. So in a database, you would say it's a table and a column. Device would be the table, and measurement would be the column. Then the time series is basically the combination of both. You see, we usually use this dot notation. I will say something about it in a minute. And then you have the concept of storage groups, which is important when running the server. As storage groups are similar to table spaces. I think they're called table spaces in Postgres. So it's physically a different folder where the data is kept. So, for example, if you put your storage groups at the right level, then you can easily split up your data later on, as it's physically in different folders and even use different threads for processing. So it's some kind of partitioning, you may call it, that you can do there. The schema is pretty simple. It's similar to the Linux file system. So you just have a hierarchy of folders where the leaf always is the measurement and the level above always is the device. But all levels above are just helping you to subclass basically. You can use them how many and how you'd like to use them. The only thing you have to keep in mind is that you have to define a storage group at some level. So in this example, you could say, okay, root.ln is one storage group and root.sgcc, or you could say root.ln.vf01 is a storage group. depending, well, it's similar to choosing partition keys, depending on your use case and how you expect the system to scale up. Okay, so now we're coming to the architecture of IoTDB. The heart or the core of IoTDB is the TS file format. Some of you may know the Parquet file format. That's a file format, a columnar file format, optimized for situations where you want to store lots of different columns, but usually read only a subset of those. So it's really optimized for columnar access. Databases usually use row-wise access. But the TS file format is even more refined. I will show it on the next slides. But this is the core. This is where all the data in the end is dumped in some binary format. And as stated previously, there is a command line interface and an API, a Java API, to work directly with those TS files. So you don't have any database at all, but just an optimized binary file format where you can store your data. And this is something you would do on a really constrained edge device, as you have no daemons, no interprocess communication and stuff. And of course, the highest possible throughput. But then there is the IoTDB server, which runs on top of TS, of the TS file format, and basically gives you all a database usually gives you. So it has a JDBC interface, has a command line interface, has a write ahead log, and all that stuff. So this gives you all the management around that. You don't have to deal with TS files and decide, okay, which TS file do I store this device or something. All this is done in the IoTDB server for you. You only insert or retrieve points via a query language, which is similar to SQL, or as similar to SQL as possible. And this server then can, there are multiple ways how to access the server. There's a native API called Session API. There's a JDBC interface. And in the next version, we will have a native MQTT interface. So basically, it defines an MQTT payload and exposes basically an MQTT server. And whenever you send the data set there, it's automatically ingested. But depending on your architecture, you will ingest data directly there or go via Kafka. For example, if you have devices all over the world which send tons of data, or via the TS file format directly. But in the end, you can import those TS files into an existing server instance. And this is, again, most efficient, of course, because you do a batch upload of the TS file once. And the TS file is already compressed and all that stuff. So that's of course, with regard to bandwidth, way more efficient than sending one request per data point. Here are some details about the TS file format. I guess all the technical details are not that important. I mean, if there are questions, I could try to answer them as good as possible. But generally speaking, they took several of the concepts from the Parquet file format. So, for example, it's column-based. So physically, in the file, it stores first one column, then second column, then third column. So if I only read one column, I physically only have to do the I/O for this column. They divide those columns in chunks, as Parquet does as well. So it's also easy to read only a subset. And then they provide natively compression and efficient encodings for multiple data types. I will show the encodings later on. And the layout they have in the file, they includes what you would call indices in the database world. So for every chunk and every column, you store some information like start timestamp of the chunk and end timestamp of the chunk. So if I have a simple query like find me the number of data points that happened in this time area, I can answer that very easily just by scanning over the chunks, by the chunk information which is stored in a header, easily. Some information about encoding and compression. Encoding first is the way how to represent given data physically, and compression is applied later on. Currently, only snappy compression is available. Encoding is pretty interesting, and you see there are multiple pretty advanced or refined compression methods used, which transform the data in a way that, or store the data in a way that it can be compressed efficiently. For example, the TS2 diff encoding is very suitable if you use counters, for example, because counters will usually give you values which have a rather fixed delta. And TS-diff does nothing else than only storing the delta between consecutive values. And if you have if you increment the counter always exactly the same, then of course you only need to store very small numbers, which you can store with only a few bits. Or and if they still are pretty similar, then snappy compression will do quite a good job. Yes, run-line encoding, which is kind of a default method, and there's the gorilla encoding, which was originally developed by Facebook, which also has some way of encoding double values which are in a similar range efficiently. So you don't have to understand all the details out here, but the key message is by applying all those techniques in the background, you can in the end store double values or integer values with 1, 2, 3, 4 bits efficiently in the end, if you use the suitable encoding and use compression. And this is something quite important because it helps you to store tons of data on your small device and on your small hard disk there. Yeah, some more examples on this adaptive TS-diff algorithm, which just help you if you have usually increasing fields, like counters are the best example, which help you then to really reduce the data size on disk, but totally transparent for you. And this algorithm is even able to handle outliers and missing points. Okay, now we're coming to the syntax to interact with. I said it's SQL-like. It's not exactly SQL, but it tries to be as SQL as possible, basically. So the first and important command that you need, of course, is the create time series command. This is similar to the create table command you see in SQL. So you give the path of your, the full path of your time series. And as stated before, in this example, S1 is the measurement and D1 will be the device automatically. And root and laptop are just the path down there. Important point is that either root or root.laptop have to be a storage group. Otherwise, the server does not know where to store it. So you have to register storage group previously. What you then give is the data type, of course, and the encoding to use. So in this case, it's an integer value with run length encoding. The insert statement is pretty equal to, or exactly equal in this situation to a database. Important is that all the values have to have a timestamp, of course. So if you do not give the time explicitly as it's done here in epoch milliseconds, then it will automatically use the current time, war clock time, when the insert command hits the server. In most situations, you do want to provide the value, as there's some random latency in between, of course. Then there's the delete statement, which again is quite similar to SQL. There is the possibility to update single values. And most important thing, of course, is query commands. And you see query commands again operate quite similar to how they operate in regular SQL. So you give it either the device with a dot star, which means select all measurements from this device, or you give it exact measurements, and then you can give it then you give it the root of those devices, D1 and D2. You have to give it the path where they are from. And then you can give conditions, and these conditions can be on values, as you see it here, or on the time, or on other functions that somehow gather properties of the time series. And there's also the possibility to aggregate queries, so count, max value, min timestamp, all those things you can easily do. And the command at the bottom is, I would say, rather crucial, and I will show it in more detail in a hands-on example, as this query is really specific to time series datasets. Because you see there's a group by statement at the end of the query, and this group by is the same syntax as SQL, or is the same identifier as in SQL, but just does something completely different. So this group by basically says throw all data sets that are within 1 hour into one bucket and aggregate them. This is the query you would like to use if you have data in the backend and want to show it in the front end, in the UI. And depending on the range the user selects, if he selects 1 day, for example, then you may decide that you only show one data point each 15 minutes. And then you would use this group by and say, okay, give me one value per 15 minutes, and for example, use the aggregate value or the max value or min value or whatever is suitable for your data type and your example. So this is one of the most crucial differences. And this is one of the main reasons why you usually need some kind of time series database. Because if you try to mimic these things with regular SQL, it gets difficult, and depending on how large the amount of data is that you have, it gets inefficient. If there are already some questions on the data sets, on the syntax, you can ask them now, but we will show them later on. Okay, Xiangdong just joined us. Xiangdong, hi.
Hi, hello everyone. Sorry I'm late.
So very welcome, very happy that you are here.
Yeah, thank you.
I already started to talk about things that you, of course, already know.
Okay, thank you very much.
And currently excuse me?
Oh, nothing. Okay, you can go on.
Okay. Yeah, I just talked a bit about the syntax of IoTDB. And I mean, from now on, you can ask basically every question, as Xiangdong is here now and is, I guess, able to answer every question that you may ask.
Yeah, you can ask any question to me.
Yeah, basically, Xiangdong, your timing is absolutely perfect, as this is an application example of a real-world application on this slide here, where IoTDB is used to basically as a replacement for Kairos DB, which is backed on Cassandra, and Xiangdong has provided this example. So probably I can talk 2, 3, 4 sentences about this example.
Yeah, okay. This application is used in Shanghai Metro, and you know the metro there are many sensors on each train, like the speed, the load, and something others. And when they use Cars DB, they have used Cars DB to store the data for about 1 year. And recently they found the disk is full, and when they want to extend the cluster, they found it is very hard to do that, because when Cassandra migrate the data from one node to another node, the cluster is almost hung up. So they connect us and try to use IoTDB. We use IoTDB. Then we have a try to use one IoTDB to manage all of their data. And now this application has been in production environment for about half a year, maybe 7 months. And now it works very well. And we just use one, like the slide says, we just use one IoTDB to manage all the data, and IoTDB can support faster query and more high compression to save the disk. Yeah.
Excellent, thank you. I mean, this is really a stunning example why you should use an optimized database, and you also see the amount of data which is generated at a single day or in a single hour, and these are the situations where you really you really get benefits from using a specialized database, because these are amounts where you would also most likely not try to use RDBMS, as will also get complicated. Tiangong, we have another question.
Yeah, I see that. Yeah.
You can probably answer from Lucas regarding Afro.
I know. I think it depends on how you define the flexible. For example, we know Parquet support nest structure, right? So if in this case, so maybe because TS file only support time series and time series data, that means there's one column called timestamp, and the data type is long, and other types can be string or boolean or integer or float and something else. So, but because Parquet supports nest structure, so I think Parquet is more flexible. But if you want to save the data in IoT area, for example, you have a device. Initially, this device has only 10 sensors, so it can only collect 10 kinds of data. But later, the device has more. The device has more sensors. You install more sensors on the device, and this device can collect maybe 20 kinds of data. If so, because when you are using Parquet, you have to define the schema before you start a TS file, a new file. But using TS file, you can add new sensors in real time. In this case, I think TS file is more flexible than Parquet. And by the way, when we use TS file, we can support the different time series on one device having different frequency. For example, you collect you collect the speed of a car by 1 second per 1 point per second. But if you collect the few remaining data, you can maybe collect it 1 point per 5 seconds. It's okay in TS file, but if you use it, you save the data in Parquet, you may have to define in a row there are some columns are null. So I think in this case, TS file is more flexible than Parquet. Yeah.
Thank you. This is something which also applies, of course, to regular relational database applications, where you always have this issue of, if I have optional points or points with different frequencies, I can never. I can technically use one table, but it will have a lot of nulls, and depending on the database, this is not very efficient. Okay, so we will go on, but if you have other questions, please feel free to just write them down. This is an overview of solutions or possibilities for your solution that you can do based on IoTDB or with IoTDB, starting from the upper left, where we may have some kind of device. We also see the PLC4X logo here, of course, because it's interesting to read data with PLC4X from a device, which you can send directly to IoTDB via JDBC or what are also set at native session API. In larger scale applications, it might be interesting to have a broker like Kafka in between or connect devices via MQTT. Visualization can be easily done by Grafana. This is a well-known tool. Nearly everybody might know it. And IoTDB provides a bridge, I would call it, which you can start separately, which connects then Grafana to your IoTDB instance. I guess there will be an updated version of the bridge in one of the next releases, but currently it's a separate process which works nonetheless.
Yeah.
Then, of course, you can just use JDBC API to work with the data, for example, when doing analysis with MATLAB or every other tool in the world which supports JDBC. And for bigger analysis, or if you need more beefy analytics, then you would want to use the Spark integration, which then operates directly on TS files, and which then gives you the full power of Spark framework. Okay, this was so far the prepared part. Oh, there's a good question from Kai.
Yes, I think it's half done.
Excuse me?
Yeah, just currently we just use a regular producer. Now we do not support the bi-directional communication, but I think it's not very hard to implement it because we have done that for Flink. We can consume data from Flink and write data to Flink, and so I think it's not very hard to implement Kafka. Maybe it's a next feature in the next release.
Yeah, I think it's a really good idea and a nice feature. So we should definitely add an issue in Jira for that. Then I think would be a nice possibility to even easier pump your data into Kafka.
Okay. So Kai said another example. So for example, we send alerts to Kafka. Yes, we are doing this feature. We call it a trigger in database. For example, you can define a trigger. Means that when your data exceeds the threshold, you can define what you want to do. Maybe send the data to Kafka or send the data to some other subpub systems, or send the email, or everything's okay. And or send it to stream pipes, something like that.
Yeah, this is something we will cover in one of the next webinars, in the stream pipes webinar. I guess we will see some stream pipes, PLC4X and IoTDB integration. Okay, so although the discussions we have are quite technical, and I know some of you really know a lot already about the projects, we start as usual quite simple. As one of the aims of this webinar is really to help people to get started with basically with zero knowledge and show them how easy it is, how it can be. So what we want to do now basically is to start an IoTDB server from scratch, show the basic syntax in a command line interface, and then I've prepared a little Java program which ingests some data, which is also available on GitHub as usual, and they will just play around a bit with it and see some examples and go on from there. So the first thing we have to do is to download binaries. IoTDB also provides binaries for each release. Then we'll extract them and just execute the start server command. I will share my screen now.
Me?
No, I prepared it already, so I will just start to share the screen. Just give me 1 second to adjust my windows accordingly. Okay. Then we can start. Okay, so Now you should see, ideally, my screen. No, not yet. So let's see. Screen. You don't see my screen yet, I guess.
Yeah.
Wait a second. So I'm back again, and I try to share screen one. Is my screen visible? No. I guess we have some technical issues. I have no idea why that is. Then let me try to share the screen now. Let's see what happens then. Okay, this screen it likes more as it looks like. Okay, then I will just share this screen. So we will start by going to the IoTDB website. Can you see the IoTDB website now?
Yeah, I can see that.
Also, excellent. Okay, so you just go to the IoTDB website, and it has a pretty prominent download button, and here are the sources, but we want to have the binaries now. So we just click on the link, we copy this download link, and I will move over to a shell. I hope you can read it. I have an empty folder, and I just want to download this file. Now it's just a regular zip file. Okay, it's downloaded now. All I do now is to unzip it. You don't have to do it in the shell, of course. It's just easier, and now it generates this folder, Apache IoTDB. If you go in here, you see the release notes, README, all that stuff, and in this sbin folders there are the scripts for running the system. So all you do now is type sbin and then start server, and depending on if you're running on a Unix system or Unix-based system or on Windows, the sh or the bat file. Now it starts up the server, and we are ready to go. So now I will switch back to the presentation for a second. So the next step we do is we open another terminal and we start a client. And with all default settings, this client will connect to my local instance. And then I will already start to fire up 2 commands to show the storage group and the time series that are already there. And well, very likely there will be no time series already there. Okay, so you may see my screen again. I open up another terminal. I again to go to the same folder and just execute sbin/start client. Now I have a client running. I'll give you an example. I prepared a cheat sheet for me already. And I start with the very simple command, show storage group. This shows me the storage groups, which is, I would say, roughly similar to database in a regular SQL server. And I can look up the time series, which is equivalent, I would say, to a table in a server. So now we want to create our first our first time series. Let's see, I probably switch them. Just let me check if you still see me. Okay, excellent. So if we want to create a time series, the first thing we have to do, I prepared already a statement, create time series. And this, now we can say show time series, and you see there's one time series already created. We can also do show storage group, and we will see that there's a storage group also created implicitly. Okay, so now we can just start to insert our first record. And this works with the syntax as shown before. This I created, going back to this command. You see, in my case, the device is called Steuerung 1, controller 1, and it has a measurement called status, which is Boolean. So what I can do now is to insert Boolean value. Oh, this is not what I wanted to paste. I can do an insert statement. And this insert statement says into the device Steuerung 1 insert the timestamp as well as the status value. And here I use the Iot DB function now. I can execute the query, and now I can try to read the value, and I just say as is equal the measurement I want to read, and I give it the device I want to get it from, and it will read the value true, which was inserted at the time here. There's a minor issue you see here, as it's not 8 p.m. For us. This is this by default uses China's time zone if you don't start it automatically. What also works here, just to show it to you, is the regular star query, which you may know. This then, in this situation, gives you the same thing, but if you would have multiple measurements in this device, you would get all of them. Okay, this is what I wanted to show you with the command line interface, and now, and now we will move on to Java, to the prepared Java program to insert some data in a batch and see some more complex queries, basically. So again, I try to share my screen. Okay, excellent, it works, and I go over to my program, and we start with looking at the POM, and all we need is one dependency, IoTDB JDBC driver. This is a default dependency. Like in every JDBC setup, you just need to have the driver. And as you see in the setup here, the only thing we have to import at runtime is a specific exception that we catch. But if we would not care about the specific exception, then we would not need to know the data type at compile time. The program I prepared is pretty simple. First, we get a connection, and I will show how we do this. We just use the name of the driver, the URL of the driver, which is regular JDBC URL string, the default username and password of my local server, and then we just call the regular driver manager.get connection to get a connection. So all regular JDBC. And if we have the connection, then we create two storage groups, which go pretty simple. We're just calling set storage group 2, and in the name of the storage group, just via statement.execute. And we will query for the existing storage groups, and then we will create some time series, exactly similar to what we did in the command line interface. I will just execute this for now. Let's see. The reason why I do this in a Java program is this is just to, oh, sorry, I did not stop at the right position. Okay, so now I have the time series created, and now I can show you something else in the, here, if I do now show time series, you see that I get all time series I have, and here I can use my basically node tree here to filter a bit, so to only see time series which are in my planned O1, or in this case I have to write line 1, then I only get those. So these three items have to be selected, let's say reasonably, to give you these features. Okay. Now I'm going down a bit, and we will look at this example. This is pretty simple example. What I want to do is to insert data for 10 days each second a day. And I insert this data into the measurement counter from device Steuerung 01, and it is a random integer value between 0 and 100. And this I do in a simple loop. So if I start the example again, it will start in this loop. It uses the JDBC batch API, which makes it a bit more efficient. And what you probably see or see not is that I just output one dot for each day to see the progress of it. But what we can do now is we can just go over to the command line interface and play a bit with those values. For example, we can say select count star, select count star from root.fabrik1 line 01 Steuerung 01. And you see that for each column or measurement, we get the respective count. My font is just so big that it's messed up a bit. But we see we already have nearly 1 million of records in there. Query again, you see my program already finished as it looks like. So the next thing we can do aggregates. Simple aggregates like the sum, for example. Okay, it already says it does not work here, so I have to give it a specific column counter, which is an integer. Now it works, and you see I get the sum of all my million values, but quite fast. And now we come to one of the unique features of IoTDB, which I already talked about, this group by, the specific time series group by. So if I want to show these values on a UI, I could of course say select counter from root.fabrik1.linien1.steuerung 01. I will add a limit 1000 here, and then I would get this. And as you see, these are way too many values, as it would just print me 1 million values, and I don't want to ship 1 million values to the front end, of course. Just for visualization. So what I want to do is to get 1 value per minute, for example. So what I do here is I write group by, and then I say 1 minute, and now I have to give the interval for this grouping, and this is something which is fixed now for the next release, but for the current release, you cannot use relative times, so you have to use the absolute times. So what I quickly do is I go to converters, and I use the epoch converter here and say I want to start with the 1st January. I take the timestamp in milliseconds. In the program, you do not do this by hand, of course. Just do it up to now, for example. This query would not work yet, as we have to give it an aggregation similar to SQL. So in our case, for example, average. So if I fire the query up now, you see that I get, as I only inserted 10 days, I get a lot of null columns. So probably to make it a bit nicer, we will also set an end date. And now I only get 12,000 result columns, but this still is too much for me. So I could say, okay, I only take 1 hour. And now I get 200, roughly 200 values that I can ship nicely to my UI. And as soon as the user zooms in, I just update the time range and make it more fine-grained, basically. Because and I can basically use every measure I want to. So I can also say, okay, I want to have it every quarter hour. It just depends on the table I want to have. This basically sums up what I prepared to show you today. And now I would like to open the session to questions, which are probably there. Just move the window to another screen. So Kai has a question, and it says, can you please explain again the relation between local database file at the edge device, or the TS file, and the Iot Db server deployed in the data center? How do they communicate with each other? And how can you just use this file as database? Xianggang, do you want to say something on that, or should I try to?
So firstly, let's explain why we say the relation between this local database file at the edge device. Maybe actually we can deploy. There are two opinions. The first one is you can deploy IoTDB on the edge device. This is the first choice, and the second one is okay. You can deploy IoTDB on your local device, and you can deploy another IoTDB instance on the data center. Then actually we have a IoTDB has a data sync model. It can sync the data file from one IoTDB to another IoTDB incrementally. So, for example, you have an IoTDB instance on one factory and another IoTDB on the data center, or maybe you have maybe you have 5 factories, and for each factory you have an IoTDB instance. So you have 5 IoTDB instances on local side, and you have another IoTDB instance on the data center. So this 5 data is the first 5 IoTDB instance. They collect data and save data locally, and they can sync the data file incrementally to the data center IoTDB. The data center IoTDB does not need to parse the data in the file point by point. It just loads the whole data file directly. Then you can read the data from this instance to read the data of the 5 IoTDB instances by using just one IoTDB instance. This is the first choice. And the secondly, actually we can if your local device has no powerful computation capacity, you can just use TS file API to write data locally, and maybe you have to send the TS file data yourself to another IoTDB instance, and IoTDB can also load the TS file directly. The second is when you write data directly to TS file, though we support read and write output stream, input stream and output stream for TS file, but you can also write something like query statement on a TS file. That's why we say we use the file as a database. You can when you read data from a TS file, you can tell your program the TS file path, or the TS file where data is, and the time source name, and the time range, and the time range, and maybe the value filter. You can define that, and then TS file API will return the data directly to you, rather than you scan the file from the first byte to the end. That's why we say we can use a file as a database. Okay.
Perhaps a short, thank you very much, Jiangdong. Excellent answer, I would say. Perhaps to give it a bit of perspective, usually when you talk to a database, then you send a question to the top layer, to the database, which then does some kind of query optimization and pushes it down as good as possible. In our case, this also happens most of the time. The difference here is that we also expose this API down, which operates directly on the file. So some operations can be done directly on the file, but some things are provided by the server, like, for example, access control. If you have the server, then you have a way for access control, which of course do not have in the TS file API. But yeah, I guess this answers the questions for you, Kai, or? Are there any more questions? Does not look so. If there are questions, here's another question about consistency. Xiangdong,
okay.
Perhaps you may want to say something.
Actually, I'm not I cannot understand these questions very well, because two users reading the same data, if there's no the third user writes data, then these two users can read the same data. It's absolutely. But maybe if there's another the third user writes data, and these two users read data meanwhile, maybe these two users they can get different data, because the first one just read 5 data points, but the second one reads 6 data points. Okay.
Okay, thank you. If there are some more questions, because our time slot basically is over already. If there are some more questions, as usual, feel free to join the mailing list. It's dev@iotdb.apache.org. You can always approach us in Slack as usual, or write an email. All I have left for me is to thank you, Xiangdong, that you took the time, although it's pretty late already for you.
Sure, I'll be with you.
Yeah, and say something next week. We will have a look into another time series database called timescale-DB, which does basically the same but totally different approach. IoTDB is basically bottom up, I would say, from the file format to the database server, and timescale-DB is top down. So it took an already existing database, Postgres, and made it a time series database. So I would be happy if some of you come again next week for some Postgres and timescale examples. I hope you took something away from it. As usual, you will get the slides, the GitHub repo, and the video uploaded so you can redo it, rewatch it, or try to mimic the examples we did here. Thanks all of you, and have a nice week. Bye.